In Chapter 13, we're going to be looking at the electrophilic addition to nonpolar pi bonds again, but this time we're going to be focusing on reactions that involve cyclic transition states. In this first video for Chapter 13, we're specifically going to be looking at electrophiles that have lone pair of electrons and how that will impact our mechanism, as well as carbenes. So first off, with the electrophiles that we add through this addition to the nonpolar pi bond, if that electrophile has lone pair of electrons on it, the intermediate that we end up producing ends up being a three-membered ring instead of the carbocation. This is trans relationship that we have within the alkene is going to be preserved in the ring. So if it was a cis alkene, the ring intermediate will also be cis. If it were a trans alkene, the ring would also be trans. We don't have the freedom of rotation around the double bond, and we also don't have the freedom of rotation around this ringed intermediate. If we have a cyclic compound is chiral, we end up producing mixtures of isomers as well. So if we actually get ready to look at this mechanism, we will start off with our alkene, which again, remember, is the nucleophile. It's the electron-rich portion. So it is going to react with an electrophile. But unlike the electrophiles we saw in previous chapters, this electrophile is going to contain a pair of electrons. So the product that we end up generating, or the intermediate that we end up generating, is going to be a ringed intermediate, where now that positive formal charge is typically going to be on the electrophile that now has two bonds associated with it, instead of being with the carbocation intermediate. If we look at this in terms of a mechanism, what we are going to see is the nucleophile will attack the electrophile, but then those lone pair of electrons are also going to come back in and attack one of the carbon atoms as well, because those lone pair of electrons are now going to be electron rich. So when we look at this, we're going to maintain that stereochemistry. So you'll notice I started off with a trans alkene for our mechanism. When I get ready to look at the ringed intermediate, we will still see that trans configuration around the ring as well. But we will still see the three-membered ring with the electrophile as part of that ring. So one of the electrophiles that we're going to see through this reaction is going to be a carbene. A carbene is going to be a carbon atom that has two bonds associated with it and also a lone pair of electrons. But because it only has those three groups of electrons, it also has a vacant p orbital. Overall, this is a neutral molecule. It does not have a formal charge on the carbon atom, but it does only have 6 electrons in the valence shell around that carbon atom. So it is very, very reactive. It is often utilized to generate intermediates, and then that will continue to react. So this carbene species is very reactive. It is going to only be sp2 hybridized. So if we look at this, we have the two R groups and the lone pair in the sp2 hybrid orbitals. We then do have the vacant unhybridized p orbital on the carbon atom as well. It is this vacant unhybridized p orbital that allows the carbene to behave as an electrophile. So even though it does have the lone pair of electrons, it is electrophilic overall because carbon is missing the octet. And it's this vacant p orbital that allows the carbene to behave as an electrophile in our reactions. So I want to look at some ways that we actually produce carbenes. They're not something that we can typically go out and purchase a carbene or add carbenes directly into our reaction flask because they are so reactive. So we end up generating them in a variety of different ways in our reaction flask. So one of the ways that we can generate a carbene is through the use of diazomethane with light. Our abbreviation or our notation for light is to use lambda times nu. So if you remember from your freshman level course, this is how we would calculate the energy associated with light. It would be equal to the speed of light, is using the wavelength lambda times the frequency, which is nu. So we'll use that abbreviation to represent that we need light to run our chemical reaction. So if we actually look at the reaction associated with diazomethane, which is CH2N2, with the alkene, the way that we would show light in our reaction is the same way that we would show that we would need heat, or that we would need to run it under reflex. We would include that H nu, or our wavelength times our frequency, on our reaction arrow. This group diazomethane with light ends up generating for us the carbene in the reaction mixture. That carbene then behaves as the electrophile with our alkene to end up producing that intermediate, that three-membered ring intermediate. This time, that E that we had in our generic reaction is replaced by that CH2 unit that would be associated with the carbene itself. So let's quickly look at the mechanism that we would be looking at for diazomethane. One of the ways that we would look at diazomethane is we would have the diazomethane, one of the resin structures would be this nice bitter ion, where we have the negative charge on the carbon atom and a lone pair of electrons on the carbon atom, at the same time that we have the positive formal charge on that middle nitrogen that has 4 bonds associated with it. So through this reaction, once we shine light on this chemical, it will break the bond between the carbon and the nitrogen. This allows us then to have our carbene generated in our reaction flask, as well as nitrogen gas. That carbene we can then react with the alkene. So again, the alkene will attack the empty p orbital of the carbene at the same time that the lone pair of electrons attack one of the carbon atoms, so that we end up producing that 3-membered ring. And again, we would maintain the stereochemistry in the ring that we had in the initial alkene. Another way that we can produce the carbene-like compound in our reaction flask is through the Simmons-Smith reaction. With our Simmons-Smith reaction, we will end up taking CH2I2 and reacting it with a mixture of zinc and copper. And we end up producing iodomethane zinc iodide. Which again is another nice organic metallic compound that will behave as a carbene in solution. So if I take that mixture and I put it in the presence of my alkene, we end up producing that same 3-membered ring intermediate, as well as a byproduct of the salt of zinc iodide. For this one, we will not walk through a mechanism. What you do need to recognize are the reagents for the Simmons-Smith reaction. The CH2I2 and the zinc copper together behave to generate that iodomethyl zinc iodide organometallic reagent that behaves like a carbene in our reaction flask.